All right, CFA Level 2 warriors, welcome to FinQuiz. If you thought Level 1 was tough, well, buckle up because Level 2 is here to test your endurance. If Level 1 was about dipping your toes into stats and regression, Level 2 is where we go full deep dive. We're talking multiple regression, time series analysis, and all the statistical tools you need to make smarter investment decisions. Sounds intense? Maybe. But don't worry, I'll break it down in a way that actually makes sense, with real-world examples that'll stick. Let's get started. Unlike Level 1, where you were mostly dealing with basic concepts and single variable relationships, Level 2 is where things get real. Now, we're stepping into a world where everything is interconnected, just like the real financial markets. And that means one thing: multiple linear regression. So why multiple regression? Because one predictor just isn't enough when you're analyzing complex financial data. In Level 1, we played around with simple regression: one dependent variable, one independent variable, nice and easy. But the real world, it's never that simple. Asset prices, risk factors, economic indicators, they all interact in ways that demand more than a one variable approach. That's where multiple regression steps in, helping us model relationships between a dependent variable and multiple independent variables. Sounds fancy? Maybe. But don't worry, we'll break it down step by step. No PhD in statistics required. So what's the deal with multiple linear regression? Well, think of it like this. If simple linear regression is like looking at a company's revenue based solely on the number of units sold, multiple linear regression is like trying to predict revenue while factoring in marketing spend, economic conditions, competitor pricing, and maybe even the CEO's mood on earnings calls. Welcome to the real world, where one variable just doesn't cut it. So, in simple terms, here we deal with the relationship between one dependent variable, what we're trying to predict, and multiple independent variables, the factors that might be influencing it. In finance, this is gold. Why? Because everything in the market is driven by more than one factor. Let's take a practical example. Suppose you're an equity analyst trying to predict stock returns. A simple linear regression might look at just the PE ratio. But in reality, returns could be influenced by interest rates, economic growth, earnings surprises, and even sentiment analysis from Twitter. Yes, that's a thing now. Multiple linear regression lets us capture all these factors in a single model. Sounds great, right? But as with anything in finance, there's a catch. More variables mean more room for error, more chances for misleading results, and more headaches for you when interpreting the data. Before we move on, folks, let me point out something that's going to seriously up your revision game. Right here on the screen, you're seeing Battle Ready Summaries by FinQuiz that are absolutely perfect for your review sessions. These aren't just ordinary summaries. They're expertly crafted, concise, and designed to help you ace your CFA Level 2 exams. Imagine having the perfect study hack right at your fingertips, designed for quick recall. Once you download and print these, you'll wonder how you ever studied without them. Don't miss out. Click the link below to grab your copy now and let these summaries drive your success. Now, let's go back to our multiple regression concept. The process is straightforward, on paper at least. First, you define the dependent variable, which is what you're trying to predict, like stock returns or bond yields. Next, you identify the independent variables, which are all the possible factors that might be influencing the dependent variable. Then you use statistical software, Excel, Python, R, take your pick, to estimate the model. Finally, you interpret the output, because software can crunch numbers, but it can't think like an analyst. That's your job. And here's the big one. Your model is only as good as your interpretation. A regression output doesn't give you investment advice. It gives you statistical relationships. Your job is to determine whether those relationships actually make sense in the real world. So, folks, the whole point of regression is to figure out how one thing, our dependent variable, changes based on multiple other factors, independent variables. And to do that, first we need to ask some key questions, just like a checklist before launching an investment strategy. First up, is our dependent variable continuous? If it's something like stock returns or GDP growth, great, we use traditional regression. If not, and we're dealing with binary outcomes, like will a company default or not, then logistic regression is our go-to. Next, does the model meet key assumptions? Think of this as quality control. If assumptions like linearity, independence, and normality aren't met, we adjust the model until it plays by the rules. Then, is the overall fit significant? In simple terms, does our model actually explain what's going on, or is it just throwing random numbers at us? If the fit is weak, back to the drawing board. And finally, is the model optimal? This is our last checkpoint. If the model is good to go, we can use it for analysis. If not, tweak, refine, and rerun. Bottom line, regression isn't just about crunching numbers. It's about making sure our analysis is reliable, meaningful, and applicable in the real world. Let's consider a typical scenario you might face. Suppose you're investigating how a combination of factors, say political stability, overall economic conditions, and ESG considerations, affects stock returns. The beauty of multiple regression is that it lets you assess all these influences simultaneously. So, how does it happen in practice? Well, same as I described earlier. In practice, you start by posing a critical question. Is my outcome variable, in this case stock returns, continuous? If the answer is yes, you stick with multiple linear regression. If not, if the outcome is categorical, for instance, you'd have to switch to a different method like logistic regression. Once you've confirmed that your outcome is continuous, you move on to estimate the regression model using your software. After the software has done its part, you examine whether the model meets key conditions. If something doesn't look right, you adjust the model, much like a business owner might tweak a marketing strategy if the initial results aren't promising. The next step is to determine whether your model as a whole is significant. If the overall fit isn't strong, it's back to the drawing board. If it is, you then compare it with other models to see if it's the best representation of your data. When your model passes these checks, you can confidently use it for analysis and prediction, turning raw data into actionable insights. Next up, the basics of multiple regression. At its core, regression analysis helps you figure out whether one variable can effectively explain another. With multiple regression, you're predicting the value of a dependent variable based on two or more independent variables. Now, if you've worked with simple regression before, you already know how powerful it is to predict one variable based on another. But what if we have more than one factor influencing our outcome? That's where multiple regression comes in. Now let's break down the basics in plain language without getting bogged down in equations. Picture this. You have a baseline value that represents your expected outcome when none of the influencing factors are present. Think of this as your starting point. Then for every factor you consider, you adjust this baseline by a certain amount based on how much that factor affects the outcome. Imagine you're forecasting quarterly sales for a retail chain. Your baseline might represent the expected sales when factors like advertising, store foot traffic, and competitor pricing are at a neutral level. If you increase advertising spend, the model adjusts your forecast upward by a specific amount that reflects how much extra sales you expect from that increase. Similarly, if rising competitor prices generally boost your sales, that factor will also push the forecast in a particular direction. Alongside these adjustments, there's always a bit of randomness, the error term, which reminds you that real-world data can never be perfectly predicted. What's important here is that each factor has its own coefficient. These coefficients tell you the expected change in your outcome for a 1-unit change in the corresponding factor, holding all other factors constant. So instead of a confusing equation, just think of it as starting with a base value and then adding or subtracting adjustments based on the impact of each factor. So folks, at its core, multiple regression helps us figure out how multiple independent variables influence a dependent variable. Think of it as building a model to explain or predict an outcome using several factors. Imagine you're running a coffee shop and you want to forecast next month's revenue. You know that sales don't just depend on one thing like the price of coffee. They're also affected by foot traffic, local events, weather conditions, and even competitors' promotions. Instead of guessing, multiple regression gives you a structured way to analyze all these influences at once. So how does this work? Let's talk about this equation. The general formula for multiple regression looks like this. Let's break this down in real-world terms. Y represents the outcome we're trying to predict. In our case, coffee shop revenue. Each X represents an independent variable, like advertising spend, number of tourists in the area, or even the temperature. The B values are coefficients that tell us how much Y changes when X changes. For example, if B1 represents advertising spend, a coefficient of 0.5 means that for every extra dollar you spend on ads, your revenue is expected to increase by 50 cents. Then we have B0, the intercept. This is essentially your baseline revenue when all other variables are at 0. And finally, there's the error term E, which accounts for all those unpredictable factors we can't perfectly model, like a sudden power outage or an influencer unexpectedly visiting your cafe and boosting sales. Why does this matter for finance? Well, in investment analysis, multiple regression is really helpful for predicting stock returns based on multiple risk factors, estimating company earnings using macroeconomic indicators, and even assessing the impact of interest rates on bond prices. It allows us to separate meaningful relationships from noise, making our predictions more reliable. The key takeaway here is that multiple regression doesn't just help us predict an outcome, it helps us understand the weight of each factor in driving that outcome. So if you're an investor analyzing a company's stock performance, this tool helps you determine whether a stock's returns are more influenced by inflation, interest rates, or earnings growth, and by how much. It's like being a detective, but for numbers. Next up, let's talk about assumptions underlying multiple linear regression. Before you start making decisions based on your regression model, it's essential to ensure that a few critical assumptions hold true. Think of these assumptions as the foundation of a building. If the foundation is shaky, the entire structure is at risk. Number one is linearity. This means that the relationship between your outcome and each factor should be straight and consistent. This means that the relationship between the dependent variable y and the independent variables x1, x2 till xk must be linear. Imagine drawing a straight line through a scatter plot of your data. If the relationship curves or zigzags, the linearity assumption might be violated. For example, if you're looking at how advertising spend influences sales, you expect a straight line relationship. If the relationship curves or changes slope at different levels of spend, the linearity assumption might not hold, and your model's predictions could be off. Number 2 is homoskedasticity. In simple terms, this means that the spread or noise in your predictions should be consistent across all levels of the independent variables. Imagine you're tracking the sales of a chain of stores. If the variation in sales around the predicted values remains the same, whether the store is in a small town or a big city, you've got homoskedasticity. But if the variation increases dramatically in one scenario over the other, that inconsistency can lead to unreliable conclusions. So homoskedasticity means that the variance of the residuals, errors, is constant across all observations. Picture a scatter plot where the spread of residuals remains uniform. If the spread increases or decreases systematically, that's a red flag. Number 3 is independence of errors. Here, the idea is that the error from one observation shouldn't affect the error in another. This means that each observation should be independent of the others, which means the residuals should not be correlated. For instance, in time series data, you want to ensure that one period's error isn't influencing the next period. Suppose you're analyzing monthly revenue for different branches of a company. If an economic event impacts one branch, it shouldn't automatically skew the results for another branch. Each branch's data should be independent to ensure that the errors remain uncorrelated. Number 4 is normality. The errors, those differences between the actual outcomes and what your model predicts, should form a bell-shaped normal distribution. What do I mean by this? Well, this means that the residuals of your model need to be normally distributed. Think of it as ensuring the noise in your model follows a bell-shaped curve, which is critical for many of the statistical tests you'll run later. Imagine you're forecasting earnings for a company. You'd expect that the deviations from your predictions cluster symmetrically around 0. This normal distribution of errors is important for validating many of the statistical tests you might perform later. Lastly, the factors you choose shouldn't be redundant. In other words, they need to offer unique information. If 2 factors are too similar, say they move in perfect sync, then your model struggles to tell them apart, which can make your conclusions murky. So independence of the factors says that the factors you include in your model should each contribute unique information. For instance, if a bank is trying to predict loan performance using 2 variables that essentially measure the same interest rate trend, well, that would be a redundant thing, folks. When factors are highly correlated, it becomes difficult to pinpoint which one is really driving the outcome. In extreme cases, if there's an exact linear relationship between 2 variables, the model cannot even be estimated. Here we have 2 parts. A, the independent variables should not be random in the sense that they're measured without error. B, there should be no exact linear relationship among them. If 2 or more independent variables are perfectly correlated, your model won't be able to separate out their individual effects, leading to interpretation issues. And folks, remember, if you detect an exact linear relationship, your regression cannot be estimated. And if the variables are highly correlated but not perfectly so, your model might still work. But interpreting the individual impacts becomes more challenging. A useful tool here is the QQ plot, which helps visualize whether the errors in your model follow that neat bell-shaped curve. If they do, you're in good shape. If not, it might be time to revisit your model setup. So normal QQ plot compares your model's standardized errors to a theoretical normal distribution. If your errors line up along the diagonal, then they're normally distributed, which means your model is on solid ground. So understanding multiple linear regression means more than just running numbers on a computer. It's about crafting a reliable tool for real-world decision-making. Whether you're forecasting stock returns, predicting sales, or analyzing economic data, grasping these concepts in a practical, business-focused way is key to success in your career in finance, and of course for your CFA Level 2 exam. All right, that wraps up our discussion on multiple regression. And if you're looking for top-tier study resources, check out FinQuiz. Their practice questions, mock exams, and detailed notes can help solidify your understanding and give you the edge you need for the CFA Level 2 exam. Keep learning, keep practicing, and keep pushing towards that CFA Charter.